Gamma ray astronomy compared to the other wavelengths developed a lot later. So it was really only in like the 60s and 70s where people started to really develop those technologies. It just wasn't there wasn't the scientific expertise until later. And so Fermi was the largest observatory at the time. It was a great mission. We went from having hundreds of gamma ray sources to now thousands of gamma ray sources. And so it was a huge step up. But still, there's a lot, if you look at a gamma ray telescope, you can't really focus gamma rays like you can do with an optical telescope. Mm-hmm. So Fermi literally just sees a gamma ray photon pass through all these layers of silicon and reads out the electrical signal that it deposits. And so from that, you get like a track of how like this gamma ray photon interacted and created other particles. And you basically just like use those tracks to point back. And the angular resolution isn't much better than the size of the full moon. So it's not really great in terms of astronomy. You think of like all these beautiful images that you see with the Hubble Space Telescope and all these things. And that's like sub-arcsecond resolution, which an arcsecond is like the best you could ever see with a telescope on Earth, more or less.
Okay.
Like if you're ever looking through a telescope, you might see a few arcseconds as like the resolution you could see with the biggest telescope, right?
And that's it.
That's it. And so that's where we would love to be with gamma ray astronomy, because you could really start to understand, you could see a lot more detail, right?
Yeah.
Things like gamma ray bursts, though, they're so far away, you're never going to be able to resolve them. Just like stars, you can never see like a star as a big blob of gas in the sky. The only one is the sun. Everything else is just way too far away. So yeah, it's a really fun time to be in gamma ray astronomy because there's so much development.
One question I have is, what are some of the undiscovered mysteries that you hope to discover more, or hope that the astronomy community finds out here in the near future?
Oh, okay. So as exciting as gamma ray astronomy is,
yeah.
One of the main science drivers for building new gamma ray observatories is that there are now all these really new fields of astronomy.
Okay.
So there's like gamma rays are developing, and we're building these giant observatories. There's also like neutrinos, which are another subatomic particle that are really fascinating. And then there's gravitational wave observatories, which are detecting gravitational waves for the first time. And both of these two like huge advances in astronomy happened in like the last 10 to 15 years. So they came after Fermi, but Fermi has been able to see gamma ray light from the sources of gravitational waves and neutrinos. And so Fermi has played this role, like studying gamma rays has played a really important role in like seeing two neutron stars in spiral together and merge together and create potentially like a gamma ray burst. And we see neutrinos coming from other, like the cores, supermassive black holes in the cores of other galaxies. And so Fermi is seeing those blazars, those incredibly like bright extragalactic sources, and can see the variability that tells us like matter's falling in and jets are being launched, and there's like interactions in the jets that are probably producing neutrinos that are traveling to us. So those two fields of astronomy are really new, and they have all these new like ideas that have come up. Understanding like what are the sources of neutrinos, what are the sources of gravitational waves. Those are like huge fields that are just opening up. So those are really exciting. And I don't even know all the questions that are going to come up, right? Every time you open up like a completely new space to discover.
New space.
Yeah, it really is, right? It's how we see space, like in all its vastness, is very limited, right? And in the last 100 years, we've gone from just having optical telescopes to like using the entire electromagnetic spectrum. And now we're like going beyond light, right? You're looking at other waves, other particles. In gamma rays, there was a new gamma ray observatory in Tibet, in China. And they've discovered like the highest energy gamma ray sources ever. And so the fact that we're seeing gamma rays at these really high energies is really exciting and interesting to me. And understanding like what those high energy gamma ray sources are is still a big question that we haven't answered. So like, are they the supernova remnants that I've been studying for a long time? Or are they these like pulsar wind nebula, which are these other things we see in our galaxy? Or are they something completely new that we didn't expect? So that there's like exciting questions to answer in the field of gamma, like galactic gamma ray studies. And then there's all the big questions in astronomy, like about exoplanets and about cosmology that like I still learn about. I go to meetings and I see all the like latest results, and it's like great to follow those too.
Wow.
Yeah. So it's really fun to go to. I mean, I haven't been to a big science conference in a while, but it's really fun to go and just hear like the huge span of topics in astronomy. Everything from like understanding exoplanet atmospheres, which is just starting now, like. I think there's been a couple like recent news releases about how the James Webb has seen different molecules in the atmospheres of exoplanets, and none of them are like the most interesting kind where we might find life. They're all like very different from Earth, but it's the first progress. Like the first planets we found were completely unexpected. They're Jupiters orbiting really close to stars, which no one thought was possible. Otherwise, they would have detected planets not in the 90s, but like in the 80s or maybe even the 70s.
Yeah.
So there's all kinds of fun. That's what I love about astronomy is you get these exciting discoveries that no one really expected, and they happen all the time. And then you get some odd results too. Like there was a while back, there was this claim for the detection of like polarization of gravitational waves from the cosmic microwave background. So they study cosmic microwave background photons, which are light that has traveled to us from when the universe was about 100 or 300,000 years old, and it became transparent to radiation. Before that, it was so hot and dense that light is almost like being inside the sun. It would move a little bit, but get scattered, and then it wouldn't really go anywhere. It'd just keep bouncing around. It would almost be like living inside, fog, right? And then all of a sudden, the fog lifts and light streams out through the universe like it is today, where you can point a telescope and see across the universe to a different galaxy. So they claim to have found like polarization in this early light, which has been redshifted all the way into radio, into millimeters. And it was like really exciting because if they had seen that polarization, it meant that there was evidence for this bizarre theory of inflation. Inflation is like this is the craziest idea in astronomy.
Okay.
Maybe as crazy as black holes. It's the idea that we live in a very uniform and homogeneous like universe. If you look out in the universe, if you look around us, like you see like, okay, there's the sun over there, there's stars over here, we've got like some structure to our galaxy. But if you look on really big scales where you start to see like where all the galaxies are, it just kind of looks like noise or like foam, right? Like the galaxies are kind of scattered in these filaments and bubbles, and then there's just really empty space between. And it all looks the same in our universe. Like if you get to large enough scales, the universe just looks completely the same everywhere. And why would that be? So the idea is, if the universe started from this really dense early point, like some big bang, and started expanding out, like eventually the universe gets really hot and really dense, and to the point where you would have like just fluctuations from the uncertainty principle of quantum mechanics, that should give more structure to the universe. Like there should be like a hot spot, like a hot half to the universe and a cold half to the universe. And we don't see that at all. We see like it's basically the same until you get to scales that are really small. Okay, really small in comparison to the universe.
Right, like, compared to the universe.
I don't know, like 100 million light years. That's a small scale in the universe. 14 billion year old universe, 100 million light years is not that much. So that's the idea that something happened really early on in the universe where all of space just like inflated faster than light, just blew up, and that smoothed everything out. And this is consistent with what we see. It's a really great theory that is like, how do you even test this idea, right? And so there's a prediction that this inflation would create gravity waves, and those gravity waves, which have been traveling out throughout the universe since inflation, would interact with like the light, the cosmic microwave background, and cause some change in polarization. And they claim to have found this, and it was like on the cover of the New York Times. And now none of my students remember that it happened because it was all wrong.
Oh, man.
And so there are these discoveries that come out that are super exciting. And you always have to be skeptical. You're like, okay, that sounds really cool, but it didn't quite seem right. It was like way higher, way more polarization than we expected. And I remember being in the Fermi collaboration, I worked with people who were in this other Planck collaboration, studying the cosmic microwave background. And so they had their own telescope that was trying to do a similar thing. They were sort of competing with the other groups. And when that came out, everyone's talking about it at a conference, and they're like, "Yeah, I wouldn't like go telling your students that. I wouldn't put too much stock in that." And they had this better data set that showed the entire sky, whereas the team, it's called BICEP2, but the team on the small telescope had only been able to survey like a small patch of sky where something was different due to the galaxy's magnetic field, and confuse their results. And so it was like a huge controversy that no one remembers anymore, because it was really only a controversy for the cosmologists, right? But it was like a really exciting idea and result that ultimately didn't like face the scrutiny of science. And I think it's such a great example. Like I still want to tell my students about this thing that ended up not being true.
Yeah.
Because every couple of years you'll hear about this like result that sounds so amazing it doesn't make sense. And a lot of the time it doesn't make sense. There was years ago there were like faster than light neutrinos. Okay, that doesn't make sense. Like neutrinos shouldn't travel. If they have mass, they should be traveling slower than the speed of light. If they don't have mass, they should be traveling the speed of light. If they travel faster than the speed of light, then they're traveling backwards through time. It's like completely bizarre. And again, there was some loose cable in a neutrino detector that ended up giving a time delay that made their speed look faster than light, and it took them forever to figure this out, but eventually they did. So there's a lot of like exciting results where you're just like, okay, does this really change everything we know about this topic, or is it going to be completely wrong? And it's so fun to be on the edge where you can, maybe if you're not the one that's necessarily like in the making the arguments, publishing the papers,
right,
but at least sharing that with students. I think that's so like, it really, I love to do that with undergrads, and they feel like, okay, they have some knowledge, they're in on the secret now, like they're beginning to see like how science works, and they have the knowledge to sort of begin to understand like how much stock should they put in.